The next unit that we're going to deal with is on limits. And in this first section, we're going to intro limits. Limit notation, we've got the limit value, and the function notation. So the way we would state it, for example, a, for instance, this is the limit as x approaches -1 of x squared. And what we're trying to do is we're trying to find values for y that approach the domain value of -1. And I'll kind of put this into context so you can see it. For letter A, we're going to use a table. It's asking us to use a table. We certainly don't have to use a table all the time if they're just asking for the limit, but in this case we are going to use a table. So -1, we're going to plug in values that get closer and closer to -1 from the left-hand side, and then we'll plug in values that get closer and closer to -1 from the right-hand side. And the way that would look is it's going to be the limit as x approaches -1 from the left-hand side, and then we're going to find the limit as x approaches -1 from the right-hand side. To substitute in numbers, we're going to plug in numbers that get really close to -1. So from the left-hand side, I'm going to substitute in -1.1, -1.01, and -1.001. Those gradually get closer and closer and closer to -1. When I substitute those into the x value in the function f of x equals x squared, I will get 1.2 for my range value, 1.02, and 1.002, and you'll start to notice that it's getting closer and closer to 1. It is true that when we substitute in -1 for x squared, we do get +1. That's a little bit of an indication that we're going to get a limit in this case of +1. But just for the sake of future problems, for example, B, it's going to be a little bit different. We want to just use a table to show the limit and show the introduction to it as well. On the flip side of that, when I substitute in numbers that approach -1 from the right-hand side, that would be numbers that are bigger than -1. I'll substitute in -0.9, -0.99. Actually, it would go the other way. So getting closer to -1 would be -0.999, -0.99, and -0.9. And when I substitute in those numbers, I get 0.8. I'm going to get 0.98, and I will get 0.998. And you'll see that that's getting closer and closer and closer to +1. So in this case, we can say that the limit as x approaches -1 from the negative side gets us +1. The limit as x approaches -1 from the right-hand side also gets us +1. Because those two limits are the same, our answer is +1. If those two limits were not the same, from the left and right side, our answer would not exist. Looking at letter B is different, and letter B is different because when we substitute in our limit value into our function, so we substitute it into x minus 2 over x squared minus 4, we end up getting 0 over 0, which is called an indeterminate form for limits. We will talk about the indeterminate form a lot in limits for sure. Because it's an indeterminate form, as of right now, we can't just find the limit by substituting in 2. F of 2 is undefined in this case, but the limit as x approaches 2, we don't know what it is yet. We're going to use some limit properties to find it. One of those limit properties is to use a table, and that's what we'll do right now. So we'll go +2, and again we're going to plug it in from the left-hand side, and then we'll go +2, plugging it in from the right-hand side. So when we substitute in numbers in this case, we're going to be substituting in numbers to the left of +2, so 1.999, 1.99, and 1.9. From the right-hand side, we'll substitute in 2.001, 2.01, and 2.1. Those range values, when we do substitute them into x minus 2 over x squared minus 4, you could use a calculator certainly to do this if you needed to, but that would get us 0.256. It would get us 0.250, and the last one's 0.25006. And again, this is undefined, but we're trying to figure out what this is approaching. It's going to get really close to a certain number. In this case, the limit as x approaches 2 from the left-hand side is going to get us closer and closer and closer to 0.25 or 1/4. I won't box that in because we got to analyze the limit first. From the right-hand side, again, 2 is undefined. 2.001 is 0.2499. 2.01 will get us 0.2494, and the last one is 0.244. So you can start to see that these numbers are gradually getting bigger, and they are also closing in on the y value of 0.25. So we're going to say that the limit as x approaches 2 from the right-hand side is 0.25. Because those two limits are the same, our answer would be 0.25 or 1/4. As we progress and go further, we're going to talk about some algebraic limit properties where algebraically we can find the limit to be 1/4. Now, example C is an example of a limit of a piecewise function. We're going to use piecewise functions a lot, certainly in limits. We're saying that the function is going to be x plus 1 when it's to the left of 1, so we can use that first when we're coming from the left-hand side. So we're going to substitute in numbers that are to the left of 1, so 0.9, 0.99, and 0.999. And we'll notice when we substitute in those numbers, we get 1.9, 1.99, and 1.999, and that makes sense because we're getting closer and closer and closer to 2. So the limit as x approaches 1 from the left-hand side of f of x is equal to 2. On the flip side, as we approach 1 from the right-hand side, we're using the other function, the bottom function. It's got a domain restriction where x has to be greater than or equal to 1. So again, when we substitute in positive 1, we get 1. And we're going to plug in numbers from the right-hand side. From the right-hand side, this will be 1.001, 1.01, and 1.1. And all those numbers are going to be exactly the same because that's just what our function happens to be in this case. Now the limit as we get closer and closer to 1 from the right-hand side, so the limit as x approaches 1 from the right-hand side of f of x gets us positive 1. And because these two limits from the left and right are not the same, we're going to write that the limit does not exist. Now that we have a basic understanding of what a limit looks like based upon a function, we're going to look at other types of limits and then function values and how they're related. And this is going to be according to a graph. So if we look at D, D is the limit as x approaches 1 of f of x. And we'll analyze the limit as x approaches 1 from the left-hand side, which is positive 1, and from the right-hand side, which is positive 1. Our limit in this case is 1. Now you'll notice that that open circle means it's undefined at 1, except f of 1 gets us negative 1. But the limit has to be the same approaching along the graph from the left and right. So in this case, our limit approaches the y value of 1 at x equals 1 from the left-hand side and also from the right-hand side. It is okay to have an open point for a limit. There's nothing wrong with that. Looking at f, f is the limit as x approaches negative 2. So the limit as x approaches negative 2, we're going to approach negative 2 from the left-hand side, and we're going to approach negative 2 from the right-hand side, and that is approaching the y value of negative 1. And you'll notice that is a solid point that we have there, even though I kind of drew it as open, but it's a solid point in there. And because it's a solid point, f of negative 2 is also negative 1. So you'll look at D and E. D and E are examples of where the function value and the limit value are not equal, and in F and G, the limit value and the function value are equal. And then one more time, looking at letter H. H, we have the limit as x approaches 5. Positive 5 would be right here. That's the y value. As we approach that limit value along the curve, we are approaching the y value of 3. And f of 5 is the solid point at positive 5. So again, h and I would be examples where the limit value and the function value are not the same.